In this problem, a single circular loop of wire with radius 5.0 centimeters is oriented in the plane of the page while a uniform magnetic field points out of the page. The strength of this magnetic field decreases from an initial strength of 4.0 Tesla at time t equals 0 seconds to a final strength of 0 Tesla. It is also important to recognize that the angle between the magnetic field vector points in the same direction as the perpendicular of the area to the loop. Therefore, the angle between these two is 0.
The magnetic field strength at t equals 0 seconds is 4 Tesla, and the magnetic field strength at t equals 2 seconds is 0 Tesla. Therefore, the magnetic flux at t equals 2 seconds is 0 Tesla meters squared. To find the magnetic flux at t equals 0 seconds, you multiply the magnetic field at t equals 0 seconds, 4 Tesla, by the area of the loop, pi times the radius of the loop squared, multiplied by cosine of 0, which is 1. The EMF then equals -1 times the number of loops multiplied by the change in magnetic flux and divided by the change in time.
The equation for induced voltage is the number of loops multiplied by the derivative of the magnetic flux. The equation for magnetic flux is equal to the magnetic field multiplied by the area multiplied by the cosine of the angle. Area for a circle is pi r squared. So, plugging in 4 minus t squared for the magnetic field and pi r squared for the area gives you the magnetic flux. Then you take the derivative of the magnetic flux and plug in 0.5 seconds for t and 1 for the number of loops. Finally, the induced voltage is 0.0079 volts.
Okay, so we are given that the magnetic field strength decreases from 4 to 0 teslas following the function Bt equals 4 times 1 minus e to the negative t over 2, and we have to determine the voltage at 0.5 seconds. So following that volts equals amp, and that's equal to n d flux over dt, we first have to find the flux, which is equal to the field times A, or the area, times the cosine of theta. But we know that theta equals 0. So that being said, d flux over dt equals dB over dt, which is the change of the field with time, times the area, times 1, which is cosine of 0. And computing the derivative of the magnetic field over time, it's equal to -4e to the negative t over 2 times -1/2. And using 0.5 seconds for t, the value is equal to 1.557. Okay, so now that we have the derivative of the field over time, we multiply this value times the area, which will be equal to the derivative of flux with respect to time. And showing that with the values here would be 1.557 times 0.05 meters squared times pi. And plugging this into the equation of Faraday's law, which would be just multiplying this value times the n, or the number of loops that we have, will give us the final answer for the voltage. So then we plug in 1 for n, the 0.05 meters squared times pi for the area, and the derivative of field with respect to time, and we get that the final answer is equal to 0.012 volts.